flavor and style of my talk will be a little bit different than yesterday. So I'm going to be talking about work in progress with Domenico Orlando and Masataka Watanabe. It's about the quantum information theory of the gravitational anomaly. No. So here we go. So, quantum information theory. It's interesting. I'll agree on that, isn't it? General properties of Hilbert spaces and tensor factorizations, which is all uses linear algebra, which all is fun and exciting, which means quantum information theory logically must be fun and exciting too. Yes. You have to admit it. Okay. Fine, maybe it isn't. Mostly it isn't, granted. You win. But okay, here we are. This is a talk about quantum information theory. We have an hour and a half. You might as well find something interesting to say about it. And what could be more interesting than something counterintuitive? And counterintuitive about entanglement. Something iconoclastic and heterodox. Right? Something shocking. That will scandalize and horrify you. Well, how about this? Entanglement doesn't exist. It's not a thing. It isn't even a consistent concept. Okay, well, I don't want to shock and scandalize you too much. So let me qualify that statement just a little bit. I don't want to say entanglement is always nonsense, just that it's usually nonsense. Or to say what I'm going to tell you a little bit more quantitatively, entanglement is generically nonsense. That is, what I'm going to tell you today is that there is a particular obstruction in local quantum field theory that renders the usual notion of entanglement between spatial regions intrinsically ill-defined in the sense that it's both formally precise and physically consequential. Obstruction sometimes vanishes, but in even dimensions, it's generically non-vanishing, and that obstruction is given by the familiar gravitational anomaly. So, that is, we're going to show that the existence of a gravitational anomaly means that there is no such thing as entanglement in the quantum field. Let me emphasize when I say that there is no entanglement in the theory, I don't mean that the entanglement vanishes in some sense between regions. I really mean that the mathematical concept of entanglement between regions of space is just ill-defined in theories with certain gravitational anomalies.
Excuse me?
Yeah.
So by gravitational anomaly, you meant pure gravitational anomaly?
I mean pure, so good question. So I'm going to focus today exclusively on two dimensions. So it lifts and has implications for other dimensions, but I'm going to focus on, I'm just going to do two, because there's enough to say about that. But yeah, so it even has consequences for the mixed case. So let me give you the statement in four. So in four dimensions with a gravitational anomaly, what it means is that with certain topologies of the entangling surface, there is no tensor factorization of the theory of the Hilbert space into complementary regions in a way that respects certain symmetries. So that's one thing that the mixed anomaly means if there's a U1 gravitational anomaly. But it tells you other things as well. It tells you, for instance, that if you compactify the four-dimensional theory on a Riemann surface with flux for a gravitational anomalous U1, again, you can't factorize the effective two-dimensional theory. But that just comes directly from anomaly descent. So, but yeah, so there are all sorts of interesting implications in higher dimensions that we're still trying to understand a bit. But yeah, so let me just focus on 2 dimensions. And by the way, this is the first time I've talked about this. I actually have no idea what people are going to wonder about or ask about, and there are papers on the topic of entanglement and gravitational anomalous CFT that are out there, and I actually expunged all the stuff in those papers from my talk, since the slides and video be on the internet. But if people ask me about those, I will have no choice but to answer. So just keep that in mind for the end, and I've left a good half hour, 45 minutes today. Okay, so anyway, but yes, so what we're going to show, yeah, is that if there's a gravitational anomaly, that there is no such concept as entanglement between spatial regions in the 2 dimensions. Right, so I really mean the concept just it doesn't make sense. So I also want to emphasize that I'm not questioning the basic concepts of linear algebra here. So our usual kind of definitions of entanglement come from, was begun by, I don't know, Einstein or Rosen or whatever that guy's name begins with P. Or that guy, bell pairs and spins and so forth. Right. So in that context, entanglement just reduces to linear algebra. Nobody is questioning linear algebra. Right. So in any separable Hilbert space, you can always find a basis and tensor factorize that basis into factors. That's not a problem. I'm only telling you that those tensor factors can't be thought of as representing Hilbert spaces living in complementary regions of space in any sense, in any approximation. So if the spatial slice is sigma is a union of A and B, then we do not have a tensor factorization of the full Hilbert space H sub sigma of the form H sub sigma equals H sub A tensor H sub B. And not only don't we have it, we don't even have it approximate. So, right, so I want to emphasize that the obstruction to entanglement or factorization I'm discussing here is not related to the obstruction to factorization occurring in gauge theories, having to do with the fact that matter lives on the vertices and gauge fields live on the links and gauge transformations live on the vertices, and there's no sort of way to exactly split up the lattice in a gauge invariant way. That is an interesting thing, and some interesting papers have been written about it already. But it's a short distance obstruction to tensor factorization, having to do with physics, within a cutoff of the entanglement sequence. That is not the sort of obstruction that's relevant here. The obstruction to factorization I'm discussing here is a long distance obstruction that's visible in the infrared. So when I say that entanglement and tensor factorizations don't exist, I mean it in that sense, with the qualifications I've given above. Oh, and by the way, I didn't put this on my slides, but I'm also going to be assuming that the conformal field theory we're looking at has all the quote-unquote nice properties. That is to say, it's unitary, and it has a discrete operator spectrum, so it's not like the Liouville theory or something. These statements all also apply to those theories, but there may be, other funny theories with a continuous spectrum that can get around this or something. But I'm always talking about, nice CFT. With all the good properties. Also modular invariance, I'll assume all that stuff. So I'm going to show you that if there is a so I'm going to show you that if there's an anomaly, then the Hilbert space really doesn't tensor factorize even in infrared, but it's sort of easier to think in terms of the contrapositive, the logically equivalent statement that if the Hilbert space does factorize, then there's no anomaly. It's in this latter form that's related to more familiar concepts that I'm going to get to in a minute, and it's easier to prove kind of directly thought of this way. So what are the more, well,
do you allow for the possibility of edge modes? So that's been coined as a possible way of getting around factorization.
Good. Right. In the category of things that have been claimed to work which don't, that's a nice, interesting one. Right. So if you have, for instance, massive Majorana fermions in 3 dimensions in a space with boundary, it sure looks, doesn't it, like that defines a nice way to kind of tensor factorize the Hilbert space of the edge modes, but it doesn't. Because the edge modes are actually strongly entangled with the massive modes in the bulk. So in other words, even the density matrix of the edge modes themselves isn't really pure. I think you'll see what other things that go wrong with that definition sort of more or that attempt more concretely. So I don't want to spoil the punchline, but so if it hasn't become clear by the end why that doesn't work, I'll get to it. So now that the obstruction to the definition of quantum entanglement is dimension specific. Okay, so I'm not talking about even dimensions. I'm not talking about odd dimensions. So the obstruction we're studying applies in the strongest form in 2 and in slightly weaker form in 6. And in 4, right, as I said, obstructs the existence of factorizations respecting certain global symmetries. So as one might expect, these are related to one another by descent. So now in 2 dimensions, the gravitational anomaly is proportional to the central charge difference, C left minus C right. So in the 2-dimensional case, we want to show that C left and C right unequal leads to an obstruction to tensor factorization, or equivalently, tensor factorization implies C left equals C right.
So I want to know a precise definition for non-factorization. What is non-factorization?
I just mean, yeah, sorry. I had to make these abbreviated to fit them into those circles in LaTeX. I couldn't figure out how to do a top thing inside one of those circles. I kept getting bugs. Anyway, just means an obstruction to tensor factorization. Impossibility of factorizing the Hilbert space into local Hilbert spaces.
So could I say it's just factorization means trivial choice?
Sorry?
Could I say factorization means trivial choice?
Right. What I really mean is if there exists any factorization of the Hilbert space into local Hilbert spaces, then C left equals C right. Thank you. Right. So now you've all been remarkably restrained up to this point. Nobody has started shouting and throwing things, but you should be. You should be jumping out of your seats by now and shouting at me that my things are wrong and that I'm stupid and I don't know what I'm talking about. Okay, so I have actually given informal versions of this talk before, so I know what's supposed to happen. But in particular, you should be wanting to tell me that, of course, the Hilbert space tensor factorizes. You've all seen these little dots. You know, people draw little dots with things living on the dots. Right? You can always draw little dots. You can see by putting the system on a spatial lattice where tensor factorization is manifest that the system obviously tensor factorizes. Again, modulo these short distance irrelevancies. Well, let's examine that idea a little bit more closely. We will see that when the gravitational anomaly is not vanishing, a lattice regulator never exists. Now, this is not a completely unfamiliar fact. In free field theory, the connection between the anomaly and the existence or non-existence of lattice regulators is an old story going back to the early days of lattice gauge theory in the 80s. So 35 years ago, Nielsen and Ninomiya proved various no-go theorems for chiral fermions in even dimensions on the lattice. So the 2-dimensional version is the very simplest of all, and let me now review the standard proof because it's so old. You know, almost nobody in this room was even born when this theory is proven, and nobody really cares anymore. But let me explain how this works. So the proof goes as follows: suppose we have a system of fermions in 2 dimensions on a lattice, satisfying canonical commutation relations like that. So here the little I is a label of the site, so these little dots that people draw. And the A and B are just species of fermions living at each site. It's an internal species label. And now consider the most general free Hamiltonian satisfying a bounded nearest neighbor property. And this is a bit of a technicality, but it can be relaxed. But this is the simplest sort of criterion for a local lattice Hamiltonian. So a Hamiltonian that's quadratic in fermions and links fermions that are a bounded number of lattice sites apart. So the Hamiltonian, we wanted to have this form. Let's make it be translationally invariant. So this Gaussian kernel only depends on the distance between the sites. So this can depend on the species, the two species labels, and the oops, this is supposed to be I, not J, sorry, and the distance between the two fermions, and then the real and imaginary parts of F are appropriately symmetrized and anti-symmetrized, so that H is Hermitian. But importantly, this vanishes when I minus J is greater than some fixed number. So now let's Fourier transform the fermion fields into their Fourier modes, which I don't know, I'll call big B. I don't know why, but I'll just call it that. Okay, so on the lattice, the Fourier modes aren't exactly momenta. They're labeled by, I forget what these are called, block parameter or something. But the point is the momentum is actually circle valued. It's not real valued. It's S1 valued because right, so if you send alpha to alpha plus 2 pi, you get exactly the same Fourier mode. So this phase e to the I alpha is just the phase difference between two adjacent sites in the mode. So then the Hamiltonian, in terms of Fourier modes, looks like this: integral over the S1 of some matrix M, which is basically the Fourier transform of this F of Fourier modes, and M is Hermitian and depends polynomially on this exponential. So now, notice that the momenta alpha, so I just said that take values in a circle rather than a real line because space is discretized. So for any value of alpha, the frequency spectrum of the frequencies of the fermions is given by the sort of eigenvalues of M. Now the modes that survive in the infrared are those in the neighborhoods of alpha space where one of the eigenvalues crosses 0. So away from 0, these eigenvalues are of order the lattice space, and they do all sorts of things. They're highly non-Lorentz invariant. But when omega of alpha crosses 0, we have a low frequency mode, something that survives in the infrared. And the velocity of each mode in the infrared, for the usual reasons of quantum mechanics, is just d omega by d alpha. Those are the velocities. But since the eigenvalues are just real periodic functions of the block parameter alpha, each eigenvalue crosses 0 from negative to positive, always has to cross back from positive to negative. So therefore, there are always exactly as many left-moving massless fermion modes as right-moving massless fermion modes. And it isn't automatically relativistic, by the way. Things have to be tuned so that they all have the same speed of light. But it doesn't matter. So if you do that, then you always have the same number of left and right moving. Oh, and by the way, we assume they all cross transversely. If they don't, if you have a double 0 or something, then you get a fermion with a non-relativistic dispersion relation. So it's impossible to get a relativistic fermion theory in the infrared with C left not equal to C right. This is the standard proof of the Nielsen-Ninomiya theorem. So this proof only applies to free fermion theories, and even for those theories, it's a little bit technical. So in particular, you have to Fourier transform, and then once you go to Fourier space, you lose a nice picture of what's going on in real space. So now I'm going to give you a new proof, a fundamentally different proof using some new concepts, but I think simpler and more elegant, and gives you a theorem with, yes, a vastly generalized version of the theorem with a very different character. And it uses real space. It applies to all interacting theories. And I think that's what's interesting about it. So I'm going to prove a highly generalized Nielsen-Ninomiya theorem, which is a no-go theorem for any lattice regulator of a two-dimensional theory with C left not equal to C right. And I'm going to do that using one intermediate concept, which enters neither the hypothesis about gravitational anomalies, nor enters the conclusion about non-existence of lattice regulators. There's some interesting fundamental concept sitting in the middle, and it has to do with boundaries. So let me explain the proof. So the structure of the proof is as follows. Consider an arbitrary CFT in 2 dimensions, and suppose it has a lattice regulator. So we're going to prove by contradiction. So from a lattice regulator for the CFT with bounded nearest neighbor interactions again, but of any kind. And then now we're not assuming they're Gaussian, we're not assuming you start with fermions. You can have Calabi-Yau valued variables at each point. You can have all sorts of different things interacting in whatever nonlinear way you like. And we can construct a boundary condition for the CFT just by virtue of the fact that we have a lattice regulator. And we do it in the most obvious way. So we just strip off half the lattice points. So the Hamiltonian in the bulk of space obviously flows to the original conformal Hamiltonian. And the boundary condition isn't necessarily conformal, but viewed on sufficiently long distances, it should flow to 1. So the conformal boundary condition, so the conformal boundary condition is unitary and energy conserving just by construction. But it's easy to show that conformal field theories can only admit unitary energy conserving boundary conditions when they have equal left and right moving central charges. So it follows that the only conformal field theories with lattice regulators are those with vanishing gravitational anomaly. So that was sort of the lightning summary of the proof. Now let's look at the details a little bit more closely. But yeah, just to emphasize, for a free massless fermion theory, the central charges are, of course, half the number of left and right moving fermions. So our proof implies the Nielsen-Ninomiya theorem as an immediate consequence, but it's more general and interesting. Okay, so schematically, we have this funny thing sitting in the middle. We go from a lattice regulator to the existence of a boundary condition to concluding that C left is equal to C right. Okay, so
Simeon?
Yeah.
Are you assuming that the theory has vanishing global gravitational anomaly?
You mean I'm assuming it's modular gravity?
Right.
Yeah, I am assuming that. I didn't write it on the slide, but I am assuming. So that was sort of lightning summary of the proof. But I mean that was it. That's really how it goes. But let's talk a bit about the individual steps, just to be careful. I don't want you to think I'm being too glib, because it sounds very glib, but it's not. It's really works this way. So first of all, why does the existence of a lattice regulator for a CFT imply the existence of a boundary condition for that CFT? So as I said, the construction is pretty simple. You start with the lattice Hamiltonian, and you just delete all the degrees of freedom at negative lattice sites. That's it. At long distances compared to the lattice scale, we have a continuum theory whose spatial slice is a half line rather than a full real line. Moreover, we've assumed the lattice regulator had the bounded nearest neighbor property, so the lattice Hamiltonian is just unaffected by the deletions after some fixed number of lattice spacings to the right of the boundary. And it follows that the bulk Hamiltonian density flows at long distance to the same bulk Hamiltonian density as the CFT on the real line, because more than 7 lattice spacings or whatever to the right, the UV Hamiltonian density is unaffected. So only the boundary Hamiltonian is unknown. Now, second, why does this necessarily give a conformal boundary condition? So I was being a little bit glib, and this is so I want to emphasize that in some sense there's a gap in the proof, but it's a very well-defined, well-parameterized gap. So this is a subtler question. One certainly doesn't start out with a conformal boundary condition, or at least not necessarily. And there's no guarantee that the boundary condition even becomes conformal by the scale at which the bulk becomes close to its conformal point. Now, at the scale by which the bulk becomes conformal, the boundary Hamiltonian might still contain non-conformal operators with large coefficients in units of the conformal scale for the bulk. Since the non-conformal operators in the boundary Hamiltonian are all irrelevant, then obviously they're going to flow to 0 at sufficiently long distances, and the boundary Hamiltonian will flow to a conformal boundary condition. No problem there. But if, on the other hand, there are relevant operators in the boundary Hamiltonian, we expect that they will give large frequencies to some boundary degrees of freedom, which can then be integrated out, leaving us with a boundary condition with fewer degrees of freedom. So this is kind of the usual renormalization group logic, and eventually one expects the process should terminate when we reach a fixed point, or at the latest when there are no boundary degrees of freedom left at all, and we should get to a conformal boundary condition of some kind. So that's the informal reasoning. But to make it a little bit more precise, there's actually a functional on the set of all boundary Hamiltonians in two-dimensional CFT called the Affleck-Ludwig G function, which is proven to be monotonic along our G flows and stationary at a fixed point. Sorry, I should have said, I didn't, but I should have said if and only if. So stationary if and only if you're at a fixed point. Now, it's essentially analogous to the Zamolodchikov C function, but with one kind of unfortunate difference. The G function is only conjectured to be bounded below. It's not known to be bounded below, which the C function certainly is in unitary theories. The Affleck-Ludwig G function isn't known to be bounded below, but it is believed to be bounded below. So the hypothesis of boundedness below of the G function has no known counterexamples in the good class of CFT, and it's strongly believed to be true by people who work on boundary conformal field theory, mostly Friedan and Konechny, who provided a lot of evidence for the hypothesis that the G function is bounded below. So under the Friedan and Konechny hypothesis, the G function has to eventually stop decreasing, and every boundary theory eventually flows to a conformal boundary condition. So from here on, I'm going to just assume the Friedan and Konechny hypothesis and just stipulate, everything in this discussion really depends on that being true. If it's not true, then there could be interesting exceptions. But it is certainly known to be true in individual conformal field theories. So they've proven it in a lot of individual cases, and it seems to be pretty true. So from here on, we're just going to assume that the Friedan and Konechny hypothesis is true, and all our derivations depend on that. Now, finally, why does the existence of a conformal boundary condition necessarily imply the vanishing of the gravitational anomaly? So that question has a simple answer. It can be understood in a lot of different ways. There are more formal ways and more physical ways to understand it, but it just follows from unitarity and energy conservation in the presence of the boundary. So the necessity of C left equaling C right, sorry, that should be equals, for a consistent boundary condition, we can see it in various ways, but the most straightforward, at least the most formally precise way, is using Carty's boundary state formalism. So, okay, not everybody knows how boundary states work, so here's what a boundary state is. So a boundary state of the CFT on the circle, a boundary state is a state on the circle, such that the thermal path integral on the interval, or the half-line, can be represented as overlaps in boundary states in the cross-channel, right? By exchanging the roles of space and Euclidean time. So, from the diagram, but so if we want to calculate the thermal partition function on the interval, so the usual way of thinking of it is this way, where this is Euclidean time, but we can just flip the whole picture and think of this as an overlap between two states with with a Euclidean time propagation of the circle Hamiltonian, not the interval Hamiltonian, connecting the in state and the out state. So there's a state associated with this boundary, and there's a state associated with that boundary, and that's what a boundary state is. But a boundary state certainly isn't an arbitrary state. So this is just what I just said. Yeah, this is just what I drew a picture of. So, blah 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 blah. So these states are boundary states because they started out before changing the channel as spatial boundaries. Now, a boundary state always lives more or less in the Hilbert space of states on the circle, not the space of states on the interval. Even though the term boundary state sometimes confuses people. It sounds like the state of the Hilbert space of a theory with boundary, but it isn't. It's a state that represents the boundary in the cross channel. And I say more or less in the Hilbert space of the circle because a boundary state is not